Hi Level 2s and welcome back to 2.5 Organic Chemistry. This is Lesson 5. So we have a fair amount to have a look at today, but it's all relatively straightforward. We are going to describe the physical properties of alkanes. So that means its melting point, boiling point, solubility and conductivity. We're going to describe the chemical reaction, so substitution and combustion, and then we're going to do a couple of practicals at the end of the lesson. So alkanes are made up of carbon and hydrogen. We've already learnt how to name them. And so we're going to talk really quickly about the physical properties. Every time we come to a new functional group in this topic, we will discuss these 3 points. So boiling point, whether they'll dissolve in water, and whether they're acidic or basic. Now, for something to dissolve in water, remember, the forces of attraction between the particles must be weaker than the forces of attraction that can form between the particle and water. So if the attraction between the particle and water is stronger, it dissolves, and if it's not, it doesn't dissolve. And the little rule we can use is like dissolves like, which means that a polar substance will dissolve in a polar substance, and a non-polar substance will dissolve in a non-polar substance. Now, alkanes are in fact all non-polar, because this is methane here. So the most basic one, that's tetrahedral. The dipoles between the slightly negative carbon and the slightly positive hydrogen cancel due to the symmetrical shape, so they're all non-polar. So if they're all non-polar, none of them will be soluble in water. And because we don't have to describe solubility in this topic, that was part of the 2.4 topic, we just need to know that they are not soluble in water. Okay, next up, acidic or basic. This is a factual thing. Something is acidic or basic, and alkanes are not. If something is acidic or basic, which we'll see a bit later on, those solutions will end up conducting electricity because ions are produced, but we won't go into this point until a bit later on when we actually come to one of the functional groups that are acidic or basic. So let's go through this in a bit more detail. So boiling points of alkanes are reasonably low. Now when we say low, it's always in comparison to other molecules. So because these are the simplest molecules, they're generally quite low, and that means that it doesn't take much energy to break the intermolecular forces between the molecules. Okay, now these are all molecules. We've done a topic on molecules. So remember, molecules are held together by intermolecular forces, and stronger intermolecular forces take more energy to break, and weaker intermolecular forces take less energy to break. There's one really significant, well, there's two things that we can talk about here that you do need to know, and that is, this is butane because there are 4 carbons, and this is 1, 2, 3, 4, 5, 6, 7, 8, octane. Now, the larger the chain, the higher the boiling point. So that's one thing that we can look at. So the larger the chain, the higher the boiling point, and that's because the larger the chain, the stronger the intermolecular forces. Okay, and that's all we need to know for level 2, that the larger the chain, the stronger the intermolecular forces, so therefore more energy and therefore a higher boiling point. So you do need to know that. Second of all is the fact that, and we did look at this in 2.4, if there's a straight chain versus a branch chain, which is this picture here. So this is a straight chain molecule. This is 1, 2, 3, 4, 5. This is pentane. Okay, 2, 3, 4, 5. And this is an isomer, a structural isomer of pentane, so the same number of carbon atoms and hydrogen atoms. This is 2,2-dimethyl-propane, and you can see here that these both have the same molecular formula, so they're really good to compare. So they're both C5H14, okay, but they take on different structures. And you can see here, this one's a straight chain, or what we call a straight chain, and straight chain can pack together far more closely, and so there's lots of surface area between them, and that means that more intermolecular forces can form, okay, and this means that collectively they are stronger. So we just say that intermolecular forces are stronger because there's a greater surface area between the molecules. Okay, whereas though here, this is a branch chain one, and branch chain ones kind of take on like a circular shape, and you can see there's much less surface area. So less surface area with a branched a branched isomer, and therefore the intermolecular forces are weaker. And if the intermolecular forces are weaker, then less energy is required to boil. So this one's got a boiling point of 9.5 and this one's got a boiling point of 36, showing that these intermolecular forces are stronger. I hope that makes sense. And you can see it across different trends. And so this is your alkanes, and this is the homologous series, so increasing by CH2. So you've got methane, ethane, propane, and butane, and you can see the boiling point increasing as the size of the chain increases. So as the size of the molecule goes up, the intermolecular forces get stronger and therefore more energy. Okay, and this one here is showing the second trend, so that was trend 1, and the second trend is the fact that a straight chain, which is these two here, have greater surface area between them compared to a branch chain, much less surface area, and therefore these have stronger intermolecular forces and therefore more energy. So those are the true trends for melting point and boiling point, and these trends hold for all of the molecules. We'll just talk about each one every time though to make sure you're fine. So if you look here, this is a wee graph of melting point and boiling point, and you can see the boiling point here. So this is the carbon number. So the boiling point is increasing with the number of carbon atoms, which is quite cool. And so I've put a question here. So how many carbon atoms are a gas, how many are a liquid, and how many are a solid? This is a bit of a thinking question. So you've got to think, well, what temperature is room temperature? And room temperature is about 25 degrees. Obviously not quite in New Zealand, but there we go. So if you get to about 25 degrees here, then between 4 and 5 carbons, it's actually 5 to be honest. So 5 carbons at room temperature. So what state is that going to be? Okay, and so that's what we're going to discuss here. And if you look here, carbon number 4, I think that's 4 here, 4 carbons at 0 degrees is boiling. Is boiling at that temperature. So boiling means going from liquid to gas, which means 4 carbons is a gas at room temperature, and then 5 carbons boils, so goes from a liquid to a gas at higher than that, about that's probably closer to 40 degrees. So that means that butane is a gas at room temperature, which means all of these must be a gas at room temperature. So methane to butane are gases. Okay, this one here, 5 carbons, which is pentane, that's going to be a gas. Okay, and same with these here. And actually, I'll talk about methane in a second. So does that make sense? So these will all be gases because their boiling points are higher than room temperature. Okay, now for something to be a solid, we need to look at their melting point. Okay, because melting point is solid to liquid is a melting point. And so if you look here, carbon 1 has a melting point of negative 200 degrees. So that means that methane will turn from a solid to a liquid at negative 200, which is crazy low. So none of these would actually be solids at room temperature at all. They're all going to be liquids or gases. So I hope that makes sense. Okay, so we've seen this before, but why I've brought up the polarity of water is so we can actually discuss solubility in water. Water is a polar molecule. It's got slightly positive hydrogens and slightly negative oxygens because oxygen is more electronegative, meaning that the electrons that are shared in this bond sit closer towards oxygen, giving it a slightly negative charge, and the hydrogen a slightly positive charge. And this separation of charge is called a dipole. Due to the fact that this structure is not symmetrical, the dipoles do not cancel and the structure is polar. Now, all of that information is marked in 2.4, so you won't get reassessed on that, but you do need to know that water is polar because it's why, and this is me going through back again, but we don't need to, which is why they won't dissolve, your alkanes won't dissolve. If you look at your hydrocarbon here, okay, your hydrocarbon is classed as being a symmetrical, is classed as being a symmetrical structure, okay, and so therefore all of these are non-polar. So even though there are polar bonds because the carbon's slightly negative and the hydrogen's slightly positive. The shape is symmetrical, so the dipoles cancel, and all of your alkanes are non-polar. Okay, so therefore, will they dissolve in water? And the answer is no, because we know that a non-polar won't dissolve in a polar. And so why is that? So if we use the example here, this is trying to dissolve hexane in water. So the intermolecular forces between hexane and the intermolecular forces between water and water are stronger than the intermolecular forces that can form between hexane and water, so it doesn't dissolve. And if it doesn't dissolve, we end up seeing layers. So you end up seeing this layer where the alkane, because it's less dense, sits on the top. So here's your alkane up here and the water down below. And so the no alkanes will ever be soluble in water because they're all non-polar, and so the intermolecular forces between the molecules, the water molecules, and between the hexane molecules are stronger than the intermolecular forces between the water molecules and hexane, so it will not dissolve. Okay, so we do need to know that. So alkanes are insoluble in water. Finally, they are not acidic or basic, so therefore they will not produce any ions in water, so will not conduct electricity. So they're not acidic or basic, they will not produce any ions in water, and so are poor conductors, so they won't conduct electricity. Okay, so the second part of this video is about chemical reactions of alkanes, of which there are two. The two types are combustion. Combustion means to burn an oxygen, okay, and substitution, which I'll talk about as we go through. So let's just launch into it. So combustion reactions are where we burn something in oxygen, and some of you will have covered this in previous year's chemistry or middle school classes, or at least I hope you have. So there's two types of combustion reaction. The first is when there's lots of oxygen available, and that is called complete combustion. Okay, now complete combustion is less dangerous than incomplete combustion, and it produces carbon dioxide. Okay, the other product that is produced is water, liquid water, but this is produced in all of the reactions. Now we actually want combustion to be complete combustion because it produces a much hotter blue flame, and it's a really clean burning compared to incomplete. So what is incomplete? Well, it's when there's not a high supply of oxygen. So oxygen is limited, and it means that you get, instead of carbon dioxide being produced, you get carbon or carbon monoxide being produced. Now carbon, which is soot, can be an irritant. It can get into your lungs, and it can line your lungs, and it can cause like asthma, respiratory problems. It can cause, it's seen as a carcinogenic, so it can be a precursor for cancer. And the other product is carbon monoxide. Now, some of you may have heard of carbon monoxide before. Carbon monoxide is a poisonous, toxic gas, and what actually happens is it binds to your hemoglobin in your blood instead of oxygen, and it's an irreversible binding. So once it's attached, it doesn't come off, and it means your body can't get oxygen, and you can actually die from carbon monoxide poisoning. And you actually see it happening quite often, where people do things like, little, those big fire like heaters that you have at bars and stuff and restaurants outside, those gas heaters. People bring those into their house because they're cold, and the problem is there's not enough oxygen in a sealed house, and so as it keeps burning, it runs out of oxygen and it starts burning incompletely, and therefore carbon monoxide is produced. So you can't smell carbon monoxide or see carbon monoxide, and so it starts binding to the hemoglobin, and people pass out, and then they unfortunately die. So this is a life lesson, that if you're ever burning a fuel, you must always burn a fuel with plenty of oxygen, never inside, because you'll produce carbon monoxide, and you actually pass out before you die, and then there's nothing you can do from there. So so a bit of a life lesson: when you combust things, you need to combust it with lots of oxygen to make sure you get CO2, a relatively harmless, there are environmental impacts, but a relatively harmless gas compared to carbon monoxide. So I'm actually going to pause this video here, and I'll come back in a couple of minutes with part B.